Welcome to Pipeline Conversations, a machine learning podcast by ZenML. Thanks for joining us again for a new episode. We took a few weeks break to reach out to some new guests, and so I think we can go as so far as declaring this next series of episodes as Season 2 of Pipeline Conversations. Today, I'm extremely excited to present this conversation I had with Ben Wilson, who works over at Databricks and who has also just released a new book called Machine Learning Engineering in Action. It's a jam-packed guide to all the lessons that Ben has learned over his years working to help companies get models out into the world and run them in production. I was really lucky to get to talk to Ben about his new book and also about the mental models that he thinks are useful to bring to bear on this complicated problem that many of us are working on. I really hope you enjoy listening to this episode as much as I did recording it. And firstly, I guess I should say thank you for writing this book. I definitely haven't finished it yet. It arrived in the mail a few weeks back. And yeah, not only is it like a dense, thick file, there's clearly a lot of hard-won wisdom and lessons and things to learn from in there. And yeah, I'm taking it very slowly and just trying to like get as much out of it from the first reading as possible.
Yeah, thanks. It's voluminous, definitely. What's funny is that if the publisher had not requested that I trim it up a bit, that book would have been more than twice as long as it actually is.
Oh, wow.
Entire chapters were removed because nobody's going to buy a 1,400-page tech book unless it's the Bible of a particular tech stack, which this is not.
Right.
So I like their decision. I think that we trimmed a bunch off. It's still fairly dense, and yeah, it's not something that you do a quick weekend read or read in an evening.
Sure.
Yeah, and it's interesting that you bring up the hard-learned lessons. I think that defines my career in tech. It's just one screw up after another. It continues to this day. I mean, that's how I learn, is by trying to figure out what the official way of doing something is. And then as everything that we do in data science and ML, you can't ever really take a demo from like API docs and copy that, paste it into code, and have your data just magically work with that. There's always some nuance and creativity that you have to do. And in the process of that, I learned a lot of lessons about things that I messed up, like royally messed up, and had to rework from scratch, or just created massive headaches for me or my team or a company in general. And I figured, why not try to capture as much of that hard-earned lessons as I could and write a book about it.
Maybe that's a kind of a good place to start for those of you who don't know who you are. Like maybe you could just talk a little bit about kind of your background in thinking about and working on these problems and how we ended up here, where you've written this book with these hard-won lessons.
Yeah, my background's a little weird. For anybody who works in the software space in general, I don't come from like straight out of university. I started working in software, or started working in data science. I was a traditional engineer, like wrenches and wires sort of engineer. Worked in a couple of factories as a process engineer and an R&D design engineer in multiple different industries. And then because I'm so lazy, I tried automating parts of my job that I found monotonous. And that led me down a path of learning about statistics and learning about applied ML. I had no idea how this stuff worked. Didn't know like how a linear regression works. I was just using it because through trial and error, figuring out, okay, how do I optimize this? Okay, they say that there's this sort of brute forced approach to an optimization problem. All right, I'm going to look at some code, bought some books, read through them, didn't understand the theory, didn't really care. It was just working. And that eventually led me to a path of getting hired at a company where that was my full-time job, was just applied ML. We didn't call it data science back then. It was just at the factory I worked at, it's called yield analysis. And a very small team of people trying to figure out mostly root cause analysis. So statistical evaluation of prior data, and drawing correlations, saying, okay, this tool at this time in this chamber with this recipe and these signal conditions caused this problem in processing of this silicon wafer. And I'm going to drop a report. I'm going to create these visualizations, provide an evidence trail file, and send that out and have some meetings and talk to people. And that that transition to a role like that was something that has defined my career since I got out of high school. Actually, joining the U.S. Navy right out of high school, I've always tried to put myself into places where I have no idea what I'm doing, and I feel like the dumbest person in the room. Uh, that fear motivates me, and makes me want to understand how stuff works and ask a lot of questions and talk to a lot of people. So moving to that factory and doing that job, I made a lot of mistakes the first year, uh, truly shocking levels of near misses, we should say. I'm like, oh, we have this issue, and I think we have, you know, 80,000 parts affected in the processing line in the factory right now. We need to scrap this equipment, this material. And a wafer scrap event at a semiconductor factory, you're not talking about like, oh, okay, it's $50,000 worth of product, or it's a couple 100,000. We'll recover from it. When you talk about scrap full line, in a factory environment like that, it's tens, if not hundreds of millions of dollars. So yeah,
Better get it right.
you definitely have to get it right. You need checks and balances. You need validation. It's not just you need a buddy to check your work. You need,
Right.
5 people to validate independently what your conclusion was, and then it goes through council review. So I learned very quickly that I needed to really understand what these algorithms and these software packages, I needed to know how they worked, because if there was an issue with how I was using it, and me being dumb and ignorant about how to properly do that, uh, we're talking people's livelihood on the line, my own employment. It's a big deal. So uh, I got pretty good at that and established a pretty sizable team at that company, and then decided to bounce off to the next unknown, and did that a couple of times to different companies in this data, now that people are calling it data science, machine learning, engineering. Uh, but I was still more on the applied data science side, just trying to solve a problem with these algorithms that I was over time getting more familiar with and understanding how to use them properly. And then moving into my job that I had right before I was hired at Databricks for a field position, uh, that was more learning how to build production capable ML at scale, where we had to build infrastructure systems that were customer facing. So we built this massive recommendation engine, and that was, REST API backed. I worked with some brilliant people at the company and on my team, and collaboratively we all worked together with the business as well to build this system. And we learned a lot, about, hey, we have a 20 millisecond budget to serve recommendations to 17.5 million people that are on multiple different platforms. How do we make this work, and how do we make it not drift in a way that's going to burn us? So that some other parts of that book, later in the later chapters, I talk about stuff like drift monitoring and A/B testing, and how to run experiments and how to constantly monitor. That's all stuff that I learned the hard way at that company. And then when I moved from there to Databricks, working in the field in post sales, all you do as a post sales engineer is work with different companies around the world. I've worked with people that are just getting started on that path, where they don't really know how to get to the first step in that 30-step process of doing production at scale ML. and I can give, wisdom to them and teach them, hey, here's the stuff to pay attention to, here's the stuff to ignore. And, you know, the pursuit of simplicity is going to be good for you. And here's how to think through that. Uh, all the way from that level of customers to customers that are doing stuff like far more advanced than anything that I've ever personally done. And they just want to run it on Databricks. So it's seeing all of these different, journeys of different companies and different teams that really informed a lot of the stuff that I put in the book.
And definitely one thing which even someone with kind of passing familiarity with the world of an ML engineer, you come away with the sense that these systems are complex, like putting ML into production and doing it like in a way that isn't just like a one-time event. Like that's a complex system that you're talking about there. I'm kind of curious, since you've written this book and you spend a lot of time thinking about how the pieces fit together, what's a good mental model of thinking about this complex system? Is there a way to make it simpler, as you were just saying?
I think a lot of people, when they think of simplicity with MLOps, think about tools first. And I don't think that's a problem per se. I think in the world of SaaS companies, uh, like both of our companies are, build tools for this purpose.
Yep.
And I think from an ecosystem of a SaaS vendor, focusing on simplicity of tools and making sure that APIs are simple to use, and it's easier to use those APIs than it is to not use those APIs. That that sort of thinking is what's needed. It's what's happened in many different software disciplines over the last 40, 50 years. And it becomes more approachable and manageable for teams. You don't have to be a savant to, take 30 different, disparate tools and glue them all together with custom code and create this, bespoke framework that works in your company's ecosystem and have a team of engineers maintaining it. It's kind of ridiculous to expect every company to do that. So the the people that are building the tools are making them simpler, and that simplifies the ML ops process or ML engineering process. But then from an applied ML perspective, like a team that's trying to solve a business problem, there's no one size fits all approach. It really depends on what problem you're trying to solve, what the actual business need is. And where I see teams really struggle who are sort of nascent to thinking about ML engineering or production ML, they focus on the tech first, and they're like, okay, here's some tools that we have to use. We need to have this in our tech stack. How do we fit this problem that the business told us to solve into this particular stack that we have? And that can create unnecessary complexity. Sometimes the team's not experienced enough to know. I mean, I would argue that no team is, air quote, experienced enough to know everything about data science and machine learning. I've never met anybody who is, and I certainly am not. It's just too broad of a topic. But there's a lot of teams that they learn something from, say, how they got exposed to data science. They do some Kaggle competitions. They see, okay, who's winning these competitions on this type of data set? What tools are they using? And sometimes there's great examples for stuff like that, or the coding boot camp that they went to for data science. They learn these approaches that work for that one use case. But in the real world, when you're talking about production ML, what you want to do is you're not trying to build something for maximizing a competition score. Nobody cares. Your business doesn't care. You shouldn't care. It's irrelevant. What you should be building for, and the mentality that I try to tell people and I try to do, is you build for production by understanding that this is something that you're going to have to maintain for potentially years. And that means you're maintaining this like before we started the recording, we were talking about a software package that just got released last night that broke a bunch of stuff. Um, that is going to happen to your ML project. Somebody's going to release a package, a new version of Pandas is going to drop, or NumPy, or some core Python language functionality is going to be hot fixed, or version is going to be deprecated, and you can't even download it from PyPy anymore. Um, when that happens, you need to update your code and fix it in production. So the simpler that your approach is, the cheaper it's going to be, not just to run it, but also to maintain it. Because if you're successful with your first 2, 3, 4 ML products that you're releasing as a service within your company, guess what? The business is going to come knocking on your door and asking for the next 7. While you're building those next 7, you still have to maintain those first 4, because that's what is making money for the company, or is saving people a lot of time and effort. And if those are unstable and flaky, all your time is going to be spent is maintaining some unnecessarily complex setup that you have configured. So that's the design pattern that I try to explain to people is, develop the simplest thing that you possibly can do. And I talk about it in the book a lot and mentioned about, hey, if you can solve it with SQL, solve it with SQL. If something you can schedule as a cron job that just executes DML statements to provide a heuristic prediction or decision, do that. I've released dozens of production air quote data science solutions where all it is clever windowing functions that aggregate data based on some set of keys and provides insight to a business unit. And the funny thing is sometimes those projects the business loves more than the super complex deep learning stuff. It's not that people are afraid of deep learning. I hear people talk about it all the time, like, oh, it's a black box. Like, well, yeah, most supervised learning is a relatively black box-ish type thing. Uh, you can use SHAP and you can use Lime and explainers to drive insight, but that doesn't explain how the optimization occurred. And but data scientists get a real big, and ML engineers, we get excited about using complex tech because it's cool. You're learning this new API and you're building something that's incredibly complex, and it just feels good when you see that finally run to completion and provide good score results. You're like, wow, this is great. Oh, but if I change this one thing, and if I take these 4 features and augment them with these other 10 features, and I create this more complex feature vector, I can get 0.2% better F1 score. And what like that path of trying to pursue excellence in prediction and making a model
Narrowly
that seems like
optimizing just one part of the whole system.
right. But as you're doing that, you're making for a 0.2, 0.3, maybe 1% gain, you're increasing the complexity of your system by 1,000%. There's so many more moving pieces that can break. What happens with that feature augmentation or feature engineering stage that you're doing when one of those features changes, which changes the distribution in a compounding way for the interacted feature. And now the model just completely goes belly up. You basically created a drift problem over time and made something that's unmaintainable. So I really try to tell people, like, hey, start as simple as possible. And the book goes through that. SQL if you can, if you have to do some sort of classification task, logistic regression is great. It's an awesome approach, and people have been using it for many, many, many years. Some very big production ML that I've seen at very big companies, they run on stuff like that because it's simple and explainable and interpretable, or use stuff like decision trees that generate that heuristic if-else statement for you. It's inherently explainable. You can print it out and show it to a business person. They'll be like, "Oh, that's what that model does." It's just a condition. It's like, oh, if it's
Either
above
that
this, then
makes
this.
complete sense or it makes no sense.
Yes. Yeah, and you could tell really quick,
Yeah,
like, oh, yeah, this is garbage, or hey, this is pretty good.
yeah.
And I tell people to add complexity when you need to add complexity. And of course, there's certain use cases that uh, I don't recommend the Luddite approach that I've heard some people tout of like, well, machine vision can be done with OpenCV and and Pillow, and you can use vector operations on the matrix of the image. It's like, yeah, you can, but if you've ever written code like that of like how people were doing you know image manipulation or image similarity through pillowing functions back in the 90s or in the early 2000s, you realize, hey, TensorFlow or PyTorch it's designed for this. Like, just use the right tool for the job. Like, do
Mhm.
you want to maintain 30 lines of code or 30,000 lines of code?
I think the tension there somehow is that this field of ML engineering, I mean, put my cards on the table, like I'm relatively new to this, so it's definitely not something I've been doing for many years and have lots of experience with. But from what I see around me, and read and so on, it feels like it's a new field, right? So there's a lot of complexity that probably 10 years from now will not exist because we've all agreed on some standards and some best practices, and there are some like libraries which get most of the things correct and all of this. And so to kind of to aim for simplicity like it can be hard in this in in an environment or a context where things are changing so much and there's a lot of flux, and so on. So if you don't have the experience and you haven't, like all of the things which contributed to your book, that if you haven't had those learning experiences, it's possibly a bit hard to make sense or make the right judgment calls in that environment, if that makes sense.
Yeah, I mean, definitely. And 100%, 10 years from now, our talk today will probably be irrelevant because people will be like, wait a minute, like this is the tool stack that people use to do
Right.
this. If we talk about BI, for instance, 15, 20 years ago, BI tools were uh, Microsoft Excel. You had, if for enterprises, you had some tooling that would generate, SVG graphics based on a very limited data set. And the comparison of how that was done, how you would generate a report then in say 2002 versus 2022, look at what it's like when you open up Tableau and connect to a cloud-based RDBMS system or to a data lake, and you can generate some very sophisticated, very beautiful, JavaScript based visualizations that are dynamic and animated. And it becomes so simple to do that, whereas before was not pleasant to build even a not so terribly nice to look at
Right.
static visualization like a crystal report. I know a lot of developer friends who used to do that back in the day and they hated it. um, but for tooling in ML ops and ML engineering, it's going to evolve to a way where 80 to 85% of all use cases, it's going to be a standard. Like, hey, we have some sort of use case that's ubiquitous in industry. Like, a lot of people do churn prediction for e-commerce, or anytime you have customers, you either do or should have a churn model that identifies customers that you should be reaching out to, or identifying whether your business is about to go the way of the dinosaurs. And those models are so common. And when you look at, if you talk to 100 different companies that are running them, the code almost looks like they copied it from each other. Yeah, sure. The naming is slightly different, but people are using the same sorts of families of algorithms. They're running it at a similar periodicity. They're evaluating it in a very similar way. So it starts to define this pattern of, hey, this is how churn is looked at. Fraud detection in banking is also somewhat similar. I mean, everybody uses different features. They collect different data about their customers, but at the end of the day, they're all using the same similar family of models with some nuanced differences. But the architecture and pipeline of, hey, we land the data in X system, we load it up, we create some features, we do some hyperparameter tuning on the model on a restricted space based on prior runs that we've done. We then, define uh, what our validation is going to be. We run that cross validation. We store the metric results. We store the hyperparameters that were used in a recorded system. Then we package this up and deploy this model. So that general architecture for sort of batch serving and also for real-time serving of a single monolithic pipeline, it's repeatable. It's, as you said, there's sort of standards being developed around that, where it's going to always be a little bit tricky to solve for tool vendors is that 15% edge case. And that's why some of the parts of the book, I actually expose how systems would be built with code examples and demonstrations. Um, that, yeah, there's tools out there that do that stuff, but to understand how to build something custom that might be a little bit outside the norm, and you might have to, write something yourself, understanding how to properly glue those components together and use stuff that's out there in the open source if you can, because you really don't want to write stuff from scratch for most things in ML engineering. It's just there'd be too much work. Um, yeah, it's kind of where I see the industry going, is trying to solve for that 85%. The 15%, there's going to have to be practitioners out there that understand how to build it, separate components for those bespoke implementations, and it'll be a chase for the industry of tooling vendors to try to go after that 15% pie, because some of those use cases are probably some of the most expensive things.
Yeah.
Yeah, like I've worked with some companies at Databricks in the field that before I had worked at Databricks, I didn't understand, or I had zero knowledge that humans were trying to do these sorts of things. It's like, you're ingesting what data? Like, you're scraping how many billions of websites every day and how many VMs are you turning on to do this? And you start seeing the scope and scale of what some companies are doing. And then you look at the size of a computing cluster that they're using to train a model, and you realize that, like, hey, that at my company, 8 years ago, we thought we had a really big on-prem data center with all of these racks. I'd walk down in there, a couple of times a week to go talk to somebody in IT and just be amazed at all the blinking lights and just how many rows and rows and rows of machines. And then you talk to this customer and see their use case, and you're like, hey, this is one project. You're using 10,000 VMs with 64 cores each. Like, what is this? How many petabytes of data are you churning through? And it's complex, and chasing down patterns for that, because everything changes when you're dealing with the difference between, a lot of people talk about ML on single machine. Like, yeah, I can build a model on my laptop and I can use, subset of training data, and it'll generally work. You want the model to generalize, not overfit. So you don't usually need a ton of data. But there's use cases out there where feeding more training data is the answer. NLP, it needs a lot of examples in order to calculate optimizations. Recommendation engines, the more data, the better, always. Uh, Computer vision, image classification, you need a lot of data in order to build one from scratch and not do transfer learning. So those use cases, it's not something that you can run on a laptop, but it's also not what most people classify as big data. Uh, a lot of our customers at Databricks are like, yeah, we got big data, and like, okay, how much data is in S3 for this data set? And they're like, oh, it's huge. It's huge. It's 11 terabytes of data. I'm like, yeah, that's not even remotely large. And they're like, what? Well, what data sets have you seen that are bigger? I'm like, I can't tell you who has, a lot of data, but I can tell you I've seen numbers that are in the hundreds of petabytes sitting on object store. Uh, that's extreme data. And if you need that as part of, nobody uses that amount of data for a training set really, but unless you're Google or maybe Meta. Uh, but for these massive use cases where you're processing that amount of data, it's not so much the code architecture that becomes the limiting point. It's the actual deployment architecture. You need to think about uh, partitioning strategies and how do you distribute data and what's the most efficient way of serializing, deserializing any object that's created in a distributed system. It becomes rather complex and I don't think many vendors are going to go after those use cases as a generic solution. So there's just not enough people doing it to make it economically viable for them to pursue that.
Right, right. So there's kind of a trend where um, kind of experts in their field are encouraged to use these new tools, which exist in the ML world, deep learning, and so on, as a way of enhancing what they do in their original fields. And I think, yeah, certainly they're not going to be working on some of these, like the 10 to 15% of what's going on, but quite soon people who are moving and kind of trying to do applied ML on some kind of case which is important to them in their particular field, they will hit this wall of complexity of dealing with a lot of these problems around putting things into production. I'm interested on your take on whether it's even realistic to encourage people to deal with the whole story, I guess. Or another way of phrasing the question would be maybe like, how small can a production ML team be?
Depends on what their consumption is. So if you had asked me this question 5 years ago of like, oh, what do you think about that term, citizen data scientist? I was one of those people that was like, I hate that term. Like data science it's not something you can just, throw data into. I've come around and I've worked with teams that it may be people that have the job title data scientists but they don't know how any of the algorithms work under the covers. They certainly don't know the mathematics behind it. um, but they can solve problems, and they're willing to learn, they're willing to fail and learn from those failures, and they're open to that pursuit of simplicity and just solving a problem. And I think setting aside job titles, which I think that the hubris that is attached to that is pretty obnoxious, and I find it rather off-putting, but we're all humans, and if we're working for a company, we're trying to solve problems, and that's all a data scientist or ML engineer is doing. um, but if you're trying to build something where you have a data set, you have a problem, you understand the business need, and you just need predictions on some problem set to be generated once a week, and it can be read from a BI tool like Tableau or Power BI to just visualize those predictions. And you're trying to say, okay, what do we think our sales are going to be for the next 3 weeks on different products? Now, if your intended audience are people that are making informed decisions about the business and they just need to have just a gauge on, hey, do we think things are going well, or are they significantly different from what we expected them to be? Then a team of two people or even one person can build that, and it's not that challenging to get something that's, kind of correct. That's perfectly fine. Uh, Contrast that exact use case where you're predicting uh, something like inventory consumption of each product that your company sells in geographic regions around the world. And then the values that are coming out of those predictions are being sent to your factory line to do capacity optimization models of, hey, we're going to because of this forecasted data, we're going to physically shut down tools and put them into maintenance mode because we don't think like the demand is going to be there, so allow 30 people to go on vacation. And when you start consuming the output of a model in such a way that reality is affected, like physical things are being affected, human lives are being touched, uh, and there's skin in the game, as I like to say. There's money on the table. Uh, then it's a different story. What happens if that forecast is 50% off? How long is that project going to stay running? Probably not that long. Maybe another couple of weeks before people get really angry. Uh, how long is that team going to be employed if the company ends up making some decisions based on their predictions that causes a 20-30 million dollar loss? Uh, I've seen entire teams get shown the door in an afternoon for a result like that. It's pretty scary. But for those sorts of use cases where there's a lot riding on it, even if the implementation isn't that complex, you're going to need a team of, not like, oh, go hire ML engineers. That's not the answer. You're not going to afford them anyway. They get paid a lot of money if they really know what they're doing. Um, but you can make something like that happen with a cross-functional team of two people from the business that are sort of on loan to work with the team for that project, or maybe they're permanent additions to that. Give them a job title of analyst, whatever it happens to be. Like, they're analyzing the result of this product that you're building. They're making sure that it's meeting the business need, and they're the final say on if there's a change that needs to be made. And you get people that have a background in data science, statistics, that can really understand the aspects of the data and be able to detect potential issues. And then you need not necessarily ML engineers, but if you're working in a company that's got all of this infrastructure and you're ingesting data, you have software engineers. Um, have two or three of them uh, work on that team. They're the ones that are working with the data scientists, making sure that the code works correctly, make sure that any custom functionality as part of that ML pipeline has proper unit testing, has a CI/CD system set up around it, that you've got, proper QA. Like, you're running something in a staging environment where people can look at changes and test them well before it gets merged to production. So yeah, it's doable with a small team.
Mhm.
Like, I've been on those teams before where there's like six people. Everybody's got a different skill set, and I actually seek out stuff like that with teams that I've built in the past, is to look for people with different backgrounds, so they can all teach each other. Everybody learns, everybody grows. If you have a whole bunch of people that all have a similar background that can all kind of do the same thing, nobody's learning very much.
Mhm.
Uh, it all of a sudden becomes more like a competition, which is unhealthy. But if you take like a developer or two developers, a data engineer, two data scientists, and an analyst, that team can do that forecasting um, at extreme scale and keep it running, provided that
Yeah,
they know what they're doing.
I was going to ask you a little bit about the role of education there, because depending on where someone's coming from, they will have better, well, certainly more experience in certain areas. So whatever, reading your book, there are certain parts of it where you can see, yeah, obviously there's tremendous value in having a really good sense of like statistical intuition about what works and what doesn't, and how to think about kind of distributions and all sorts of these things. But a software engineer, just like that, probably wasn't part of their training, at least if they came up from some kind of traditional background. So
Hmm.
it seems like cross-functional is the way to, as in, don't expect your software engineer to have great statistical intuition. That's kind of what you're saying, it seems.
Yeah, it's not in their wheelhouse. If they want to learn it, great. Like, don't tell somebody like, "Hey, you can't work on this because you're a software engineer and software engineers don't deal with statistics." That's obnoxious. And I actually see companies do stuff like that. It's like, why would you do that? It's they're not a different species. They're they're a human being who's very intelligent. You hired them because they're very intelligent and they're very capable at what they do. They can learn other things. Um, so I never, in any team that I've been a part of or that I've led, or, or organizations that I've advised uh, in my current or in my previous role, um, I always tell people that, like, hey, get some professional diversity in this team, and further on that, get some cultural diversity as well. It People don't sometimes don't think about that. They think about job titles, and they're like, "Whoa, we need to get a, if we want to do cross-functional background, we need to get a software engineer and a data engineer and some data scientists." And sometimes I've told people, I'm like, you need to get people from different backgrounds too. You can't get a whole bunch of people that grew up in Manhattan in New York City, or a bunch of people that grew up in Palo Alto, and expect that they're going to have differing viewpoints. They grew up in the same environment. They matriculated through university at probably the same school. They didn't get exposed to different ways of thinking through things. Get people from different backgrounds, from different countries, from different cultural backgrounds. They will make a, a much better product. And that's been proven out. I don't know how many times in Silicon Valley, of looking for that diverse global talent pool and picking people from different backgrounds to put them together, and they make magic happen. Same thing should be done in a data science team as well, because I would argue that it's even more important for data science use cases, because like software engineering is creative in the sense of you're solving logical problems in unique ways, or you know there's a lot of disciplining and structure around that, because you have to, it's got to work.
Yeah.
It either works or it doesn't work, and it's got to work. So you need a lot of controls around that. uh, Data science and even some aspects of ML engineering, there's a lot of creativity in there. Sometimes you're going down a path that nobody's tread before. You have this unique idea of how to do this thing with data, or how to combine this feature engineering processing with this model architecture. So it's a very creative process, and it's also a business focused process. A software engineer is building something for use by a client or internally at their company, and they're almost like a consultant that works within the company. You're just delivering something that people are asking for, and it has to meet these product requirements, and it just has to continue to work. Whereas data science is, hey, we have this problem we need to solve. Nobody knows how to solve it. If they did, they wouldn't be talking to you. And it's very creative and potentially frustrating, because you're going to try 100 things and 99 of them are going to be wrong. Hopefully one of them is going to be correct, and you have to creatively do that. So the more diversity that you have in technical background as well as cultural background, uh, you just get different viewpoints on how to solve something. And I've always found those teams solve more interesting things faster and more reliably than a team of monocultured, mono job title, mono background individuals.
Not to mention, I guess, like probably a more, yeah, diverse team is probably going to going to help you spot some of those edge cases and things and like failure modes that a monoculture team just it wouldn't occur to them to think of. Yeah, along the way.
Yes, definitely. Yeah, if you get enough similar people together working on something, it almost becomes like a hive mind. It's really weird. I've seen it before. I've actually been in those teams before. It's very surreal. Like that nobody objects to anything. People just conform to whoever the loudest voice in the room is, and it it's not healthy. It doesn't work very well. You don't build really good products or solve really interesting things. People just conform, and I think that's human nature. If you're around people that are very similar to you, it it's almost like a psychological projection that you are them in some way. Whereas if you have an incredibly diverse but also open and uh, sort of collaborative environment of people from different backgrounds that you grew up in a different part of the world, you your first language that you spoke was a different language. It's a different way of thinking through the existence and reality of life that gives you a different perspective. And having a little bit of contention with viewpoints is what creates great software, great product. Uh, and yeah, I always seek that out, and I always recommend that others seek that out.
I think someone who comes to your book, it's a technical book from Manning, like it has this title, Machine Learning Engineering in Action. They might be surprised to when they find that something like 1/3 or maybe as much as half of the book is about like organizational and non-technical things. Could you talk a little bit about, where you come from? I'm totally on board with that decision, but might be seen as surprising.
Yeah, that was something that I didn't think was going to fly at Manning either, because I've got dozens of Manning books. They're all technical. They write really good books. Like their authors are great. They go through this process of establishing this template of, hey, this is how we write these books. This is the structure. I went through that as well and butted heads a little bit at the start. But I pitched it to them and I said, hey, yeah, the technical aspects of data science work are important, but those books have been written so many times before. There's some great ones out there. And I listed off a bunch of them to them. I was like, here's something I have in my library. I've learned a lot from them. I think they're great. But in practice, in doing what I've been doing for the last decade of my life, um, that's not the whole story. In fact, you can have such high technical excellence in data science and ML engineering and never get something that stays in production for more than a month. I've seen it. I've seen it many times actually, at both big and small companies. Talk to somebody, sit down, look at their code, and you're just like in awe almost, like how elegant it is and how well it solves the problem. And then you ask them like, well, how long has it been in production? They're like, oh, they just told me to turn it off. I'm like, well, why? Like, why is it getting turned off? And their response is, well, they don't think it's important. I'm like, you didn't sell it to them. You didn't sell this idea to them. And they're like, well, can you work with me? Can you tell me how I can do that? And I'm like, no, that ship has sailed, man. Yeah, like they're not emotionally invested in this. They just see this as some genius at their company sat in a closet in the back of the office space and built something amazing that they don't understand and they don't care about. This project could make your company a 30% lift in revenue, but you're never going to find out because you didn't involve them from the start. So that's why that first, yeah, it is somewhere between like a third and a half of the book is mostly focused on communicating to a technical audience how important, sort of like product management skills are to a data science team, to a tech lead, to an ML engineer, to anybody that's working on that team. It, it is not a job or a profession that it's not like software engineering where you're expected to take a list of requirements and build a prototype and demo that prototype and gather feedback in this back and forth sort of way. Like, hey, we're going to release this new version. Can you please check it out? Data science isn't like that. There's too much at stake. It costs too much, and it's potentially too disruptive to the business to expect that something that's even it's potentially brilliant in implementation and expertly executed is going to ever be adopted by the business unless they have skin in the game. Now, you involve them early on in the process of planning stuff out and get them excited. You now have people that are going to bat for you to the executives saying, hey, we really need this product or this project, and we're going to devote 3 of our people to work with the data science team, and they're going to QA everything. They're going to give feedback. They're going to be the testers for this. They're also going to help, we're going to, and then you get the back end data engineering team. They get involved and excited about it because they're like, wow, somebody's using our data for something cool. Yeah, we're going to devote one person 50% of the time to support the team with whatever they need. Oh, you need ETL written? Yeah, we'll do that for this project. You build a village around a project and you'd be amazed. I've seen just complete hot garbage of code. Like, you look at it and you're like, how is this running? Like, how is a computer actually processing this without just saying, nope, I'm not running this code? But it's running in production. There's a team of 40 people at even a mid-sized company. Everybody believes in it. They're doing talks on it. They're not showing code during the talks, but you know they know how bad it is. But the company believes in it. They're writing blog posts about it, and it attracts greater talent to the company because ML engineers and data scientists see that and they're like, whoa, that company's doing something cool. And they're putting ML first. Yeah, I want to work there. So it's a conscious decision. It's a smart decision for companies to do that, and bringing in that diverse outside talent of more experience to work in that culture. It's transformative for a business. If a company can figure that out, that's how you leverage ML and a data science team. So that's why I wrote so much about that process, because it's so critical for successful ML.
Yeah, not really covered in so many places, I would say. So it's definitely like a useful addition, I would say, if someone from Manning is listening. I appreciate it. Do you have any kind of, I guess there's a lot of new entrants to this field and space. Do you have any kind of early-ish career advice for people who are trying to be more competent, more productive with this kind of the whole story of machine learning engineering? What's the, either in the technical side or in the kind of that organizational communication side?
The organization communication side, I would say, uh, adopt Einstein's methodology. You give it an hour to solve a problem, take 55 minutes to ask questions. Be that person who's asking the questions and listen to people who others might dismiss at a company. If you're new to a company and you know that, like, oh, I got to do this, this project for the ops department. Well, everybody told me to not talk to marketing and not talk to sales, but I'm going to go see if I can, talk to them and see what they know about this product. The more people you learn to talk to and listen to and distill their needs and their opinions and their viewpoints into a cogent, cohesive project plan, the better off you're going to be. So that's a big piece of advice. Just talk to people and listen. And ask way more questions to the point of annoying people is what I recommend for an ML project, and keep it up as well. Like, don't just do a one-off discussion, and make sure that you're capturing their ideas and they approve of how you're capturing their ideas. And then from a technical side, I'd say don't skimp on software development skill set. You don't have to know how to build like framework code or infrastructure. You don't have to know how to build ZenML, the open source toolkit as a data scientist. You should not, you shouldn't be that good of a developer as a data scientist, because if you are, then go do software engineering. You're probably going to make more money in the long run, and it's going to be a different experience if you're already that skilled in that. unless you really want to do data science work. Um, but you should be competent enough to write code that doesn't break and that is testable, and know how to debug something pretty efficiently, uh, and know how to be able to read code as though you're reading your native language. That's a skill that's very important, particularly when you move from that first position and go to your second job or your third job, probably at a different company. If you want to, start making more money, that's how you do it is move
Yep.
from company to company. And your second job, you might not be expected to know a ton, but by that third or fourth or fifth job, when you're, an L7 or an L8 as a data scientist in a company, you're expected to be able to look at a project's code in GitHub and just sort of understand how it works without having to run stuff, without having to look stuff up. You should be able to do a PR on somebody else's data science code and provide valuable feedback. You should be able to identify code smells of bad architecture and code and problematic structure. And all of that is, you learn as you do. You learn from reading books, you learn from practicing. And then the third aspect that I recommend that people do is try to solve problems. And that doesn't mean try to solve a Kaggle competition or something like that. Those are valuable, and there's a lot of great open source data sets out there. But you don't have to solve stuff with a computer to start learning, you know, how to do data science. A lot of data science is thinking through how to solve a problem. Uh, think about
And
what the
communicating
passions that,
about it, I guess.
yeah, communicating about it as well. But for problem solving in general, I always ask people, when people have asked me that before, like, well, how do I get good at figuring out which algorithm to use and what data to use to solve this problem? Because when you're working on a new project, people are usually like, hey, here's the database, or here's the data lake. And you're like, okay, which of these 83,900, columns of data across 16,000 tables am I going to use to solve this problem? Uh, Being able to distill a problem and understand what data to use, it's just general thinking, like critical thinking skills and problem solving skills. So I always ask people what their passion is, and whatever their passion is, what do they do on the weekend? Um, are they really into like fixing up old cars? Well, see if you can disassemble the engine in your head without physically looking at it, and see if you can diagnose what problem might be if you observe this. You start asking questions of them, or have them just do those exercises of thinking through, like, hey, how does this thing that I engage with in my off time, how does it actually work, or why does it work the way it does? And those thought exercises, I've found, when I've done that mentoring technique with people in the past, they've actually come back to me 6 months later and said, those tasks that you had me do back then, about thinking through my framing of my photography, of like my nature and wildlife photography that I do on the weekends, that's actually helped me in, thinking through some of the problems that the business comes to us with. I'm like, yeah, I know. That's why I mentioned that to you. Like, you can train your brain to observe reality in a way that it's sort of like solving a problem in whatever task that you're doing. Maybe you're mowing a massive lawn on the weekend. Well, try to think through what the most optimal path is to go through your yard where you're not discharging dead grass in clumps on the yard. What is that pattern? Think through that. And those approaches, that's what a lot of data science work is, really, is solving problems that are very ambiguous. A lot of software engineering is like that as well. So those are my 3 tips to new people.
Very nice. So we usually end with a couple of quickish questions, or as short or as long as you'd like. So the first, what would be a quick win that someone can add to make their productionizing of models or their project more robust?
More robust, quick win. I'm a fan of your guys' product, actually. Use something like that. If you have the ability to, template out and introduce, model provenance and tracking and, understanding how to actually construct pipelines in a way that you can reproduce the code and execute arbitrary places in it. That's probably the quickest win, and building it from scratch sucks. So there's open source tooling out there. Definitely use that.
And what would be one part of putting a model in production that you feel needs to be given more attention by tool makers in the space, that something that's forgotten or not really being handled at the moment?
I think people are working on it, but it's the thing that burned me the most building like production ML is drift monitoring. And not just drift monitoring. A lot of people are talking about that now, and there's a lot of really cool open source products that are addressing this right now. But the question that every serious data science tech lead should be very afraid of is when your CTO or your CIO or your CEO comes down to your desk and says, "Hey, how much money did that model make us this last quarter? I just got the bill for the cloud costs based on this tag. So it cost us $180,000 to run this for 3 months. Can you tell me how much that made me?" If you don't have that attribution set up before you went into production, you are totally screwed. That is a monumental scramble of work of trying to do post hoc analysis on something that you probably didn't have cohorts set up to even do that measurement. You didn't have long running A/B testing with some sort of holdout. And because that data doesn't exist, you're going to have to do some number fudging to try to answer that. Because most people aren't going to say, "Hey, boss, I have no idea how much this thing made us." You're going to come up with some number. If they fact check you later on, they find out that you made something up, time to update your resume and maybe change your field of profession. So yeah, that was something that I learned the hard way. I was the one who said, "I have no idea, but I'm going to create a way to find out, and stick with me." Luckily, the person who was asking that question was understanding enough to say, "Let's work together on this." And we came up with a plan of how to do that for the use case that we needed. But it's not trivial, and it's very custom to the business. But I think that tooling makers are going to get there, probably within the next 5 years, of creating a framework to do this exact thing. It's just not a lot of people are talking about it right now. But everybody who's serious about ML, they do it. You have to do it.
Yeah, I mean, from the way you described it, it sounds almost like a kind of a behavioral or a kind of an all-encompassing thing that you need to kind of have around the edges of what you're doing. But yeah, that would be great if there was a tool that could help you think through that, for sure.
Yep.
Yeah. Well, great. Thank you very much for coming on. And yeah, everyone who's listening, I hope will go and read your book slowly and digest all of the many lessons and things in there. Yeah, I certainly am going to continue doing that myself.
Awesome. It was an absolute pleasure. And thanks for having me on, Alex. This was really fun.
Thank you for listening to this latest episode of Pipeline Conversations. If you enjoyed what you heard, please consider giving us a review wherever you get your podcasts. It helps us get seen by more people, and of course, it's always nice to receive feedback. If you have suggestions for future guests, please send them over to podcast@zenml.io. Thanks. Until next time.